At this moment, we've finished our discussions about the first law of thermodynamics for control volume and also for closed systems. We derived the equation for each kind of system. For a closed system, we derived first law, and it was really short. It was Q minus W equal to delta E. And then we also derived first law of thermodynamics, but for a control volume, and that one is much longer. Either way, for both of the systems, first law of thermodynamics is just conservation of energy equation. Energy cannot be created or destroyed. That's what first law of thermodynamics says. So now we're moving to the next part of this class, second law of thermodynamics. So in addition to first law of thermodynamics, there is a second law that we have to follow in our designs. The first question is, what is second law? How do we express second law? We have three options. We can express second law in three different ways. The first way, it is impossible for any system to operate in such a way that the sole result would be an energy transfer by heat from a cooler to a hotter body. This is the scientific language of the first option to express second law. In short, what does it mean? Heat cannot be transferred from low temperature to high temperature if you do not pay any work. If things just happen naturally, heat must transfer from high temperature to low temperature, not the other way around. That's the first way to express second law. Second law tells us there's a direction for the process, from hot to the cold, not from the cold to the hot. That's option number one. Option number two, when we express what second law says, is Kelvin-Planck statement. It is impossible for any system to operate in a thermodynamic cycle and deliver a net amount of energy by work to its surroundings while receiving energy by heat transfer from a single thermal reservoir. This statement seems to be long. We can explain this by one example. Let's recall a power cycle. You can think of the engine in your car as the example. What happens is you burn the gas, so you generate heat. Heat will go inside the engine at a high temperature. We simulate this process as a heat transfer process. Heat transfer happens from high temperature TH to the engine. And then you want to convert as much of QH to mechanical work, W cycle, as possible. You want to convert as much as of the heat, QH, into mechanical work, W cycle, to drive your car. If there's only first law we have to follow in our design, which is conservation of energy. Can this design be true? Yes, this design will be true. You can just say total energy going in, QH, must be equal to total energy leaving. So QH is equal to W cycle. If first law is the only law we have to follow in our design, then this equation is true, which means the efficiency is defined as W cycle over QH. It will be equal to 1. If first law is the only law we have to follow in our design, then the efficiency of the engine in our car will be 100%. And we know it will not happen. Why is that? Because we have to follow first law and second law. We have to follow first law and second law. What does second law say? Second law says you cannot work if there's only one single thermal reservoir, meaning TH. You have to lose heat to a lower temperature. Think of the exhaust coming out of the engine. It's still hot and it just goes to the environment, which is at a lower temperature. What is happening is the engine is losing heat. We call it QC. To a lower temperature, we call it TC. Second law says QC will never be zero. You have to lose heat. If that's the case, let's go back to first law. Total energy going in, QH, must be balanced by total energy leaving. In this case, I have two terms leaving. They are W cycle and Q code. And Q code will never be zero. And from here, we can see energy, if the efficiency will be still defined as W cycle over QH, and W cycle this time will be rewritten to QH minus QC over QH. So it becomes 1 minus QC over QH. Because QC will never be zero, so the second term QC over QH will always be greater than zero, which means efficiency eta will always less than 1. That's why the efficiency of an engine in the car will always be less than 100% because we have to follow second law of thermodynamics in addition to first law. That's the second way to express what the second law says. And then lastly, we have option number three, how to express what second law says. It's called entropy statement. What is entropy? We will discuss about entropy in chapter 6. You can think of entropy as a property that we use to describe the direction of a process. It is impossible for any system to operate in a way that entropy is destroyed. We use capital S for entropy. Capital S is the letter we use for entropy. You can think of entropy as your age. You will never become younger. Your age will only become bigger. So is entropy. Entropy can only become bigger in this world, and that tells us the direction of a process.